So good morning or good afternoon, wherever you are in the world. My name is Dan Fabbri. I'm an associate professor of biomedical informatics and computer science at Vanderbilt University Medical Center. And today I'm going to be talking to you about BRIM. BRIM is infrastructure for AI-guided chart abstraction. And I'm really excited to tell you about the work we are doing today at Vanderbilt, as well as the work we are doing as part of a company called BRIM Analytics that has been spun out from the research we have done at Vanderbilt in partnership with ARPA-H and other institutions. To start, you might be asking, what is BRIM and why even name it BRIM? Some of you might be aware of REDCap, a data capture software system that was developed over 20 years ago at Vanderbilt. BRIM is an ode in name to REDCap and kind of continues down some of that tradition of NIH funded research to then bring out tooling that can be used across the nation to make research and operations and care faster and better. My goal for today is to start with a slide presentation where I kind of outline what BRIM is, how it works, what problems we're trying to solve. At the end of the session, we will have a real life demo, as I think it's important to take AI technologies and put them in front of the user to make them understand how the system works, and so how users can use the technology and make sure people understand the actual practical use case versus slides. As part of that process, as we go along, you have access to the QA functionality within the Zoom chat. So if you have specific questions you would like answered, please feel free to post them, and I will try to answer them as we go along. And please feel free to shout out as we go along. Overall, my goal today is just to share some of the work that we're doing at Vanderbilt. And interestingly, some teams at Hopkins have already been using BRIM for their work and will share some of the exciting progress they've made to date. So to first start, I just wanted to start with a local problem we have at Vanderbilt that I think is relevant to a lot of the organizations or large academic medical centers across the nation, which is one related to surgery management and planning. And I'm going to be talking specifically about a population of patients initially right now at one age spectrum, obviously pediatric patients in this case, but obviously this applies in similar sense to the aging population and managing surgical risk. At Vanderbilt, we have a ambulatory surgery center. This is a lower acuity surgery center that treats a lot of our patients for lower risk care. This is a type of procedure you might expect, like for tonsils and adenoid removal, or other low risk cases. CMS and other organizations demand that you cannot have high risk patients treated at these facilities for a number of reasons. One, we don't have the necessary other care providers available for high risk situations. And we don't have the ability for patients to stay overnight. And our ability to treat severe acute issues is limited. And so for that reason, Vanderbilt and a lot of other surgery centers who are trying to move patients from their main surgery center to these ambulatory surgery centers to open up space in their main OR and increase their efficiency of their outpatient facilities have to balance this risk of how do we do it safely? How do we ensure that high-risk patients are not scheduled at these ambulatory surgery centers? And unfortunately, high risk is defined by many criteria. In our case here, the definition for an exclusion criteria for a patient at these ambulatory surgery centers is if they have a range of criteria, whether they have ASA 3 or 4, whether they have any type of cardiology referrals, whether they have sleep apnea or recent flu, whether they have a history of CF, whether they're insulin dependent, whether they're morbidly obese, if they have a first or second degree relative that has bleeding disorders, if they have sickle cell, and actually the list goes on. If they have cirrhosis, if they have any suicide ideations, if they have any type of chromosomal abnormalities, or have any type of pacemaker. These are all excluding criteria that prevents individuals from being treated at these lower risk surgery centers and must be scheduled at the main campus. But what you're probably noticing here is a lot of these details, the specific chromosome abnormality, if there's a first or second degree bleeding risk, those are not details that are actually in structured metadata in the clinical document. They're actually in clinical notes. sprinkled among pages and pages of text, especially for some Alzheimer's patients or patients with long-term care. This can be tons of background information, and finding this information can be slow, tedious, and cumbersome, and often results in errors. And so, what is the current practice today? The current practice today is at Vanderbilt for this one surgery center, we actually have four nurses whose job is to go through the clinical note, identify if a patient is high risk based off any of those criteria, and if so, reschedule the patient. For 500 patients a month, for one clinic, it takes four nurses over 300 hours. Let me say that again. 500 patients, one clinic, over 300 hours a month, and that's one clinic. We have many, many other clinics that have the same workflow across the organization, and you can imagine how it takes time. It distracts the nursing staff from the actual patient care responsibilities and can be really challenging. But at a high level, this is not just a problem for this ambulatory surgery center. What really is the problem that we experience across healthcare today is the need to take these large volumes of unstructured clinical notes and oncology notes on radiology reports, ER visits, uh, home notes, home care documentation, et cetera, and convert it to actionable structured data that can be used in clinical trials, quality, research operations, and registries. This conversion of transforming unstructured clinical notes to structured form is paramount to getting a lot of the work we need to get done in healthcare today done, but is a step that is not often forgotten and currently is done by human effort. And that human effort is often referred to as manual chart abstraction, the process of poking and pecking through clinical notes to find relevant content. It may be a task that takes 5 minutes to 60 minutes per task. It may require hundreds, if not thousands, of charts to be reviewed for a given task a year or month, and it may cost $50 to $100 per hour for that person to do this. These are often skilled nursing staff, for example. This is time consuming, it's expensive, and error prone. And you can imagine how the cost of this type of process across the organization, from research to operations to trials and operations, is extensive. And this has downstream effects, right? Your impact of chart abstraction being a bottleneck reduces or causes burnout in staff, requires them to do extra work. It limits throughput and opportunities for identifying the best care pathway for a set of patients. And for clinical trials, for example, we see that there's a drastic reduction in potential cases of patients that can be matched for clinical trial pre-screening, and we lose the opportunity to match some of these clinical trial patients to actual trials because it's so hard to read some of these cases. And so our goal with BRIM, in partnership with Vanderbilt and ARPA-H, which we were lucky enough to receive funding from the ARPA-H initiative in the last couple of years, is to build an AI-guided chart abstraction system that allows organizations to transform clinical notes into actionable data for any given chart abstraction task that the organization might have, whether it's for oncology registries to orthopedic injury due to pickleball. We want the system to be flexible. Now, a lot of you might be saying in the background of your head, chart abstraction sounds great. Why can't I just use a large language model to solve this problem? And why isn't that just the answer? And we agree that large language models, the OpenAIs, the Anthropics of the world, provide one of the greatest new foundations to streamline this process, to take unstructured clinical notes and put it into a structured form. But we view that token production system of OpenAI, for example, as a modern day engine, for example. The LLM is an engine. It allows you to go down the road. But it really doesn't give you a steering wheel-like interface to answer complicated questions such as, did this person have Alzheimer's? Have they had previous falls? And other types of issues, and then determine the timing of events and other complicated issues like that. How you can orchestrate this, review the results, manage it gets cumbersome. And so what we see happen across institutions over and over the years, or last few years for AI systems, is that people build and use large language models in a one-off ad hoc process today, where they'll load their data from the clinical EMR or other record, they'll define their prompts themselves, they'll write their own Python scripts to abstract data and review the results. They'll run it, they'll deal with rate limiting and context window, they'll try to decompose the task into various steps, they'll review the results by maybe sending it off to a colleague. And then once they've completed that, then they'll put it into production. And from there, once they do that, they'll then need to do it again for their next task and the next task and the next task. And we see a lot of organizations rebuilding or repeating this process over and over today. It's brittle, it's not repeatable, it's slow and hard to collaborate. And so we find organizations wasting time and effort to build chart abstraction at scale. Moreover, some more people will tell me, why can't I just take my large language model, take the fanciest language model out there, Opus 447, for example, give it all my patient's notes, give it my clinical trial document, for example, and have it produce its results. And for small, simple questions looking for, does this patient have Alzheimer's, that may be sufficient. But as you get more complicated chart abstraction tasks, the question comes up about, how do I debug the issue? How do I ensure the traceability of the results? As complex criteria for clinical trial matching or other registry information occurs, how do I deal with complex criteria and the nuance of that data? How do you scale the results from one patient, which is easy to do with an LLM, unlike ChatGPT, but scale to 1 million patients and run it for every patient in the organization? And then how do we validate the results in a consistent way going forward? The other big thing that's really, really important is, how do we manage privacy? How do we ensure that someone just doesn't take a patient's medical record and throw it in the public open AI, but uses the appropriately approved institutional AI endpoints, for example? So in summary, we think LLMs actually do provide that amazing foundation or computational engine for abstraction, but for operations, trial, screening, and research. But there's limited, fast, and repeatable infrastructure available today, and as a result, we see a bunch of one-off scripts for LM chart abstraction and incomplete prototypes. So what our objective with BRIM is to provide the repeatable infrastructure for an organization, much like a steering wheel on top of the car, for anyone in an organization, student, faculty, and staff, to grab that steering wheel to be able to define the criteria for their chart abstraction protocol, quickly iterate and review the results, adjudicate the results, and then with the same system, deploy it. This democratization of chart abstraction, from requiring someone to know how to program, dealing with context windows, etc., allows a whole new range of individuals across the organization to participate in this work. It allows individuals to define their nursing criteria and abstract it for themselves. It allows a researcher to grab the wheel and do it themselves. And it takes projects that previously were taking years, now are possible to be done in days, if not weeks, as well. Under the hood, though, what's really important is this abstraction, the steering wheel-like interface over the large language model has to deal with all the complexity of dealing with the large language model. Rate limiting, RAG, hallucination guardrails, prompt optimization, context windows, self-introspection. These are all extremely nerdy things that are necessary to make large language model extraction successful, but are complicated, difficult to get right, and are rebuilt over and over across project and project. And so with this steering wheel-like interface, we want teams to be able to grab the wheel, extract the data they want, and move on to actually solve the important problems at hand versus doing that infrastructure. Moreover, many of you, as we get a little nerdy here for a moment, might be thinking, okay, I've seen large language models, I've heard about that. I've also probably heard about fine-tuning large language models and building models specific to a specific use case. Thus far with BRIM, we've used is known in the community as foundation language models or foundational LLMs. Those are the OpenAI GPT-5 or 4, the Anthropic Haiku or Opus. These are models that are general purpose, not specifically fine-tuned on a specific task, and have general reasoning capabilities. Over the years, we've looked at using many different types of fine-tuned models, but we've found that the cost to train individual models for each use case, from pediatric cancer to orthopedic injury, requires a bunch of manual effort and time and care and cost, versus what's called in-context learning that allows organizations to give some examples and get really good results. We're also a huge believer in what's called mini models. So that's your mini models in OpenAI or your Haiku models in Anthropic that allow you to process billions of tokens at hundreds of dollars of pricing, so thousands of patients. And these allow us to scale the analysis greatly. If you were to try to use the most fancy models for all your patients, you would run up a tremendous bill, and that's not feasible. So really what we're really excited about is the combination of these foundation models with in-context learning. And as those models get better, our performance actually increases along the way. It's important to note that why do we think democratization and the need for repeated infrastructure is so important? A recent study at MIT said over 95% of AI pilots fail. What we actually argue is that we don't know where AI is going to work in an organization today. Will it work for an Alzheimer's care group? Will it work for pediatric cancer? Will it work for orthopedic injuries, et cetera? We don't know. We don't know what workflow, what clinical trial, what research project will work for it. But our opportunity here is if we have repeatable infrastructure that allows us to test hypotheses quickly and adjudicate results and move forward, we're able to try a lot of things quickly. We're able to fail without feeling pot committed to continuing down the project if it's not likely to succeed. And it allows us to explore options that we otherwise couldn't try before. And so this is why we think having general purpose infrastructure for chart abstraction within an organization is so important, and why organizations like UCSF and others have deployed BRIM institution-wide. So what does BRIM look like in terms of a data flow? At Hopkins, for example, BRIM is deployed within the Hopkins Azure environment. So it's in your secure environment. No data ever leaves using Hopkins Azure OpenAI endpoint. Again, no data ever leaves to use an LLM, and it's using your approved LLM endpoint. Data are loaded from Clarity or loaded from your Databricks or other data warehouse into BRIM, and then you define what we call variables to define the concept that we want to abstract. BRIM then provides the interfacing on top of the LLM or generative AI model with the charts and the variables to then define the abstraction result, as well as produce raw text evidence for every result that's produced. So not only are we producing evidence of why they have cancer or did they have a fall, but also the raw text in the note used to produce that result. At the end of the day, what we end up having is a structured data output that can be used in downstream processes, loaded back into Epic, used for your research projects, etc. This can all be done manually, or it can all be done through a RESTful API, so you can trigger the job of chart abstraction on an automated schedule going forward. So what does this look like in practice? A variable in BRIM is kind of our atomic unit of work to abstract data. As you will recall, I told you a little bit about mini models. These are smaller, less capable LLMs, but are quick and more effective. We define a variable in BRIM to be a unit of chart abstraction. We want to abstract one thing at a time, perhaps cancer progression or scan site. And we might want to abstract data not just from one document, but it might be from across multiple documents or from within a document. So one of the big things that comes up that people don't often understand when dealing with chart abstraction today is when you do chart abstraction, there is a temporality to it. You have one document, then a second document, then a third document. You have an order of events. You need to figure out where that information came from, what is the most recent information, et cetera. And so you need to compare data across information. And because we're using focused LLM tasks, we're able to dig specifically into a specific document and compare across documents to create, for example, aggregations about cancer progression or aggregations about scan sites. So in our view, a variable here is the atomic unit of abstraction. It has some set of instructions. It has a concept of scope of how we aggregate data, whether it's across documents or across a patient. It has some type. It also has potentially dependencies. So one variable can be abstracted to feed into another. So here we have three documents. Maybe we abstract cancer progression, maybe we abstract cancer start date. But then the results from these individual chart abstraction tasks can now be fed into a higher order clinical trial inclusion criteria that allows LLM reasoning across that. And so what's really exciting about this is that this kind of building block approach of decomposing the abstraction tests into atomic units, abstracting each individually and then combining it together, allows us to express some really complicated logic for chart abstraction. For example, in the most extreme case, we deal with a lot of clinical trial chart abstraction. What does that look like in practice? We will view a clinical trial as a big tree where the dependent variable at the top is the patient eligible or ineligible for a given trial. Underneath that is a bunch of different data points that the team must abstract to determine eligibility. And underneath those might have individual data points that are abstracted from the record that need to be brought up. You can see with a complicated structure or a complex clinical trial that doing this type of review can be complicated, that if you get it wrong or the LM gets it wrong, you need to have the provenance or the traceability of a result to dig into where the result may have erred. And you need the ability to quickly adjudicate results across complex logical conditions. And so this is really, really important to have this type of interface. So to make this example more concrete, imagine you have a breast cancer clinical trial and you want to determine if a patient is eligible for a drug. Here is one of 31 criteria for eligibility. The patient is eligible if they've received taxane in a neoadjuvant setting, can be treated with the same class of chemotherapy if it's at least 12 months have elapsed between the completion of treatment with curative intent, date of primary breast tumor surgery, or date of last neoadjuvant chemotherapy administration, whichever occurred last, and the first documented local or distant disease recurrence. First off, that's a mouthful. Second off, you realize the complexity that we are asking our nursing or research coordinators to review clinical notes to abstract data from charts. How many different data points need to be abstracted here? Did they receive taxane? When did they have their last curative treatment? When or and if did they recur? Has it been 12 months? These are all different units of abstraction that need to be done to determine eligibility. With Brim, our goal is to take that text and first convert it into a logical plan of how do we want to go about abstracting that data. And then with that logical plan, abstract all the data points individually from the chart and then raise that information up into the tree to get the final eligibility criteria. And to be clear, here we have this eligibility for these drugs. You have prior taxane as one variable. You have 12 months elapsed as another variable that's dependent on the date of curative treatment. And then you have a date of recurrence. And so this individual value has one abstraction task with an LLM. This individual value has one abstraction task with the LLM. Their values are combined to determine 12 months elapsing. You have another variable for prior taxane, and then all those results are combined together. This decomposition of chart abstraction tasks is so important to the success of work in reading and reviewing clinical notes today. Moreover, what's really exciting is that once you define this abstraction protocol, it can be shared across sites. So why is this important? If Hopkins right now is working on for example, a cancer registry protocol for abstracting data, you can define the variables once with their instructions and names, and for example, share it to Vanderbilt, or share it to CHOP, or share it to UCSF. And by doing that, you can just define your logic for abstraction, share the variables definition, and any instance running Brim can now execute that abstraction protocol in a consistent manner across all these sites. Brim, or this metadata model, allows you to define the concept of what you want to abstract, and then the actual execution of the abstraction is managed by the execution layer in Brim itself. And so we're really excited about now running multi-site clinical trials that can now define the protocol once and then execute it multiple times across multiple institutions and aggregate data so that we can create larger cohorts of data going forward. So how has Brim been used today? Brim is now deployed across the nation from Hopkins, from CHOP, from UCSF, from Vanderbilt. In some organizations, Brim is now deployed at what's called as a research core service. So as part of the CTSA or CTSI, the institution launches Brim as a resource for any faculty, student, or staff to use the tool for chart abstraction where the system loads in clinical notes and then the user can do chart abstraction. At Vanderbilt, we've had over 100 different teams use Brim to date. And at UCSF, we've had over 100 different projects or teams also use Brim as well. And so this is really exciting. You know, some colleagues at UCF said, from my perspective, Brim is solving the right problem and is by far the best way to do chart abstraction at UCSF today. This is really exciting. We're exciting. We started this as a research project. We've now built this infrastructure and tooling that can run completely in your own organization. Data doesn't need to leave. And now it's often used as a core service where anyone now can do their own research, run operations tasks, or do clinical trial pre-screening independently. So we've seen Brim used across a range of use cases. And so really what we're excited about with Brim here is that it is not just built for a specific individual use case. It's not built for one registry. It's not built for a specific cancer use case, but it's flexible from Alzheimer's disease, for dementia, for orthopedic injury to cancer clinical trial pre-screening. And this flexibility really allows us to operate across the institution and really bring value to organizations who are currently bottlenecked by some of the largest notes in an organization and trying to make sense of all the data to date. So going back to the initial example that we started with, we talked about this use case for this perioperative ambulatory surgery center, where we wanted to ensure that we weren't scheduling patients to the ambulatory surgery center that are also high risk, and we had a range of over 30 different criteria. Well, when we actually deployed BRIM and used this at Vanderbilt over now, I think 6 months in real world deployment, we saw the team that was previously taking over 300 hours doing their work can now do this process in 4 hours in a given month, all with 99% agreement between BRIM and the nursing staff. And this was one of our biggest kind of aha moments when we're like, wow, we can define a range of criteria for chart abstraction and make it work and answer complex logical, do complex abstraction for, family bleeding history, recent flu, looking for any chromosomal abnormalities and the like, and doing it effectively across the organization. We also had a group that was trying to phenotype older populations of patients at Vanderbilt. They were specifically looking at Lewy body patients, looking at some of their past history of care, and looking at analyzing a large population of patients to create a large data set to do both drug discovery for an aging population, as well as looking at opportunities for drug repurposing going forward. And to do this work, normally the team would look and analyze, a few patients or tens or 100 patients. But our real goal with this project was to analyze hundreds or thousands of patients, to get bigger signal out of these patient cohorts than we currently are doing today. And that's just limited by human capacity. There's just so many patients. It takes, so long, or 5 to 7 minutes to read and review every patient's chart. It's not possible in some cases to do thousands of patients for a given Alzheimer or Lewy body dementia population. And so for those reasons, we wanted to see, can we scale this process using BRIM? And so we defined a few variables, one for Lewy body dementia confirmed, the existence of an MRI or CT for that, the existence of an EEG, and any existence of any psychotic medications. And each of those tasks individually we're taking a few minutes to review, go through a huge history, click around Epic within the note. With BRIM, loading that data and doing the review was significantly faster on the order of reducing time by 90%. And we saw 99% agreement with the humans. What was interesting is when we did a retrospective review of human versus BRIM inter-rater reliability, there were a few differences. But then when reviewing those, we found in many cases that the human abstractor had erred because they'd missed some relevant data points. And so one of the interesting things is using AI and other AI tools to make sure we have extremely high sensitivity in our results, and then allowing the human abstractor to adjudicate those results if it's ambiguous. And I think that's one of the big lessons we've learned about this work is how do we build tools and technology that allow our currently highly skilled staff to work at the top of their pay grade, to be as efficient as they can and not be bogged down by monotonous tasks. Similarly, we've done some work at the Children's Hospital of Philadelphia where some of our collaborators were working on low-grade gliomas. Obviously, this is a younger population than the group today we're speaking to, but they similarly, this population had a range of cancer types, and the group at CHOP wanted to abstract data from their EMR, analyze it quickly, and create a repeatable process for abstracting those data and compare it to human results. And when we looked at that pediatric neuro-oncology data set, we found F1 results of 0.95 and above for one cohort and one set of fields. And then when we looked at specific genetic alterations and the specific genetic alterations that were being identified, we saw about an F1 score of 0.8. This was work that was presented last year at the American Medical Informatics Association. And what's really excited for us about this type of work is we provided the CHOP team with Brim, and within their environment, they loaded the data, did the abstraction, and did the analysis independently of us. And so providing them this tool, this capability, allows for tremendous opportunity for work going forward and to speed up manual abstraction tasks. In addition, some of our colleagues at Hopkins have actually been using Brim over the last year. Within the Cancer Center, um, uh, various groups have been using Brim at Hopkins to do a range of chart abstraction tasks from analyzing stage of cancer, whether it be TNM, histologic grade, margin, tumor site, or oncotree, among others, and using that to compare retrospectively on what human-based labels were produced. And what was really exciting about this is that with a few iterations of improvement and optimization in Brim, Brim was able to get about a 96% accuracy with human labels. And this was really exciting because we were able to kind of, again, just provide the Brim software to the Hopkins team, let them kind of kick the tires and build chart abstraction tasks, and then really quickly review the results and iterate. And I think this is a really, really important thing. Chart abstraction is so foundational to clinical care medical practice that having to reset up this process of abstracting data and the pipeline and the review and the validation over and over and over just bogs processes down. And if we can make that process repeatable, the opportunity to do more work quicker, more effectively is just tremendous. And so with that, what I want to do now is pause, first ask for any questions, and then I'm going to convert over to a demo to actually show you how this works in practice. So I'm going to pause real quick, stop sharing my screen, see if there are any questions in the Q&A, and then I am going to jump over to the screen. All right, Q&A is going. There was a question of, have you compared Brim with Rectifier, the AI with Care at MGB? We have not had the chance yet to compare that. I would love the opportunity to compare. The Rectifier tool, I believe, is similarly doing clinical trials matching and pre-screening. And from my understanding, it's a great piece of work and software. I don't know enough about it beyond the paper I've read. And published in their proceedings. But I think it's a great opportunity for collaboration and would love to learn more. All right, I'm going to share my screen. All right, I'm now sharing my other screen, and let me know if you cannot see the new demo page. Okay, I'm now presenting the demo of the Brim software. What my goal in the next 15 minutes really is to show you all a little bit of how Brim works and to give you a high-level idea of how a person would do chart abstraction in Brim. The first point you might be wondering is, so this is a Brim piece of software. As I stated before, it runs entirely within your healthcare organization's environment using your organization's approved LLM endpoint. So within Hopkins, using Azure, using the Azure OpenAI endpoint, so no data ever leaves your tenant. Moreover, Brim is a project-based workflow, meaning that the system can have many projects. Each project can have its own set of data, its own schema for abstraction, as well as its own team of users to collaborate. Why is this important? You have one Brim instance now with many projects, and that allows you to facilitate your work across an institution in parallel. My goal today is to start with an empty slate for Brim. To start with nothing loaded into the system, I had just gone ahead and created a project. And what I want to do now is show you from start to end how you could go about abstracting data in roughly 7 minutes. We're going to go through the 4 major boxes of Brim, from project setup to generating results to reviewing results and exporting data. So to begin, we're going to start by loading some data. In Brim, you can load both patient notes, so a CSV of unstructured clinical notes that comes from Epic or Databricks or the like. You can also load data, structured data like the date of a surgery or ICD codes or other structured data. Or date of birth. You're right. There's no reason to use an LLM to extract data if it's already available. And everything also that I'm showing you can also be done through an API. And so there's a full RESTful API on the back end of this to facilitate that. So what I'm going to go ahead and do is just upload some clinical notes. This is just going to be a very simple example for this demonstration. But the point here is I've loaded a set of notes. Here we have a set of patients, and each patient has a set of notes. And here we have a patient that's a 49-year-old female with HER2 negative, ER positive breast cancer. And at this point, if you were doing a chart abstraction, your objective might be to read the notes. Your objective might be to identify, do they have cancer? Do they have HER2 negative or ER positive breast cancer? Have they had radiation? Are they on adjuvant chemotherapy? These are all the type of things that a chart abstractor might have to do, and that would take time and effort to do. So in Brim do you define the variables for abstraction? So in Brim, a variable is our unit of abstraction, and there's a number of different ways you can create a variable. You can create it by hand. You can upload it from a library. We have a set of pre-built variables that you can use for trauma or NSQIP or other diagnostics that are available that if you wanted to just use those variables directly, you can. Or you can upload them in batch or load them from RightCap. So I'm going to start as simply as possible by saying, does the patient have cancer? Obviously, this is a very simple example, but the point here is I want to just walk you through it and end a use case. So here, a variable has a set of fields. The field for their variable name obviously is there. That has a type, whether it's Boolean, integer, float, a timestamp. And then really importantly, it has a scope. A scope defines the granularity by which we are abstracting data. Do we want the granularity of the data we abstract to be one per patient, i.e. did the patient ever have cancer? Or do we want the value for us to abstract to be one value per node, right? To look, for example, at cancer progression over time. Or we might want many labels per node, i.e. looking for every individual medication administration. So these are all different scopings that we can choose to define how we want the system to work. And then you have your instructions. These instructions are run on every document, and much like a prompt, they provide your details of how you go ahead and execute. You have some other semantics here, like defining the default value if no information is available. And then really importantly, one of the things I think is often missed is how you aggregate data across a patient's medical history. Right? If a patient has multiple instances of documentation of cancer, where does that come from? What if there are two instances, which one do you use? And do you take the let's see, there's a question that popped up. Do you turn true if any value is true? Do you turn the earliest date, the latest date, the most frequent value, return the value from the latest date, the count of all values, or you can even have custom instructions to deal with aggregation. This is really important if you want to take data from multiple parts of a clinical record, combine it, and adjudicate the results. In this case, we're going to just say, I'm going to return true if any value is true, and go from there. All right, so now I have this variable, does the patient have cancer, and it's defined. There was a question, can this be adapted for real-time clinic visit or pre-visit prep? When was the past treatment done? What are all the family medical histories, et cetera? Kane, that is a fantastic question. And yes, we actually have some folks using this, for example, to prep for their cardiac TAVR clinic. That it's not real time per se, but we get the set of patients that are scheduled for the week and we load it on Monday morning, all the patients that are scheduled for the week to determine have they had any stents, have they had a TAVR before, what is the size of any of the devices implanted, et cetera. And that's done to prepare for a clinic. And so, yes, all that's done in prep for a visit, and it can be similarly configured in a kind of real-time fashion. There was another question from generalization is really exciting. Can this one run into generalization how do you map this from one institution to another? We're actually doing a lot of this work now where we run the abstraction protocol from one site, share the abstraction protocol to another, and evaluate them. But I think the question there really comes to how easy is it to translate definitions of variable from one site to another? And with Brim, that is a force class thing that is required. And so actually in Brim, you can actually share variables as easy as sharing a file. And with a couple clicks of a button, you can now have variables defined. You can have a variable for cancer progression. You can have a variable for cancer evidence defined. If we click on edit for cancer progression, you can see it has a one per note variable. It has some instructions, and you can see it has improving, responding, progressing, worsening, stable, mixed as options. But really what's exciting about that is literally within a couple of clicks, I can export my variables and I can share it with someone else. And they can load it into their Brim instance and run it directly. And this is why we are excited. Because now the process of defining your semantics for chart abstraction is as easy as defining a variable, potentially exporting it and sharing it to someone else for them to load it and run it. And this now allows us to make this process much more quickly, more easy. So at this point, we've uploaded some data, we've defined some variables, and now we're going to generate results. This is this steering wheel-like interface where, for example, I want to generate on two patients for all my variables and generate some results. Under the hood, what Brim is doing a bunch of different steps to review the results, aggregate the results, validate hallucination checking, tie results together, track your token usage, all together as one, and then produce for you essentially a draft chart abstraction for the team. And so why is this so exciting for us is now within a few clicks of a button, you can go ahead and start reviewing results in the note. You can say, all right, for this patient, variable cancer progression has a value progressing, worsening, enlarging. And here is the raw text used to produce this label. You can now click on this link and it will jump you directly into the note where this result came from. If you like the result, you can accept it. If you don't like it, you could edit or remove it. And so now the process of chart abstraction can be one of reviewing small snippets of text. Maybe you can look at the reasoning for why the system made a determination, the presence of a lesion, for example, or growth indicates worsening, etc. You can accept the results and move on. You can also use these labeled results to improve the system over time and optimize variables. Thus, in a few clicks, we've now generated some results for a set of patients where you can go ahead and click and review all the results for individual patient by document, or review all the results by variable. At the end of the day, though, what we've done is essentially generated a sample abstraction protocol in file where we've now essentially built a sample abstraction data set with our variables, our MRNs, our date of birth, our variables on the top here in a matter of minutes. And so this is really exciting for us. You can literally define your product, upload your data, define your variables, click abstract, get the results, and go and move forward. Pausing for questions. I'm done with those two. Okay. But that's Brim 101. You might be saying, okay, cancer progression, you looked at one value, that's easy enough to do. But what happens if you have more complicated phenotypes? What happens if you need to do something more complicated? What if you need that tree-like interface to determine cancer site eligibility for, requiring or cancer trial eligibility that you have to have a certain age, you have to have cancer in the breast, and you have to have cancer? Well, Brim allows you to reference other variables that are abstracted. Again, this like tree-like design where you now have they're eligible for this trial if they have cancer, cancer sites includes breast, and age is greater than 17. You can now use and reference these other variables you've abstracted. So now when we go ahead and review the results for a given variable, and we click on review, now you can see both evidence for has cancer equals true, cancer sites is in the breast, and their age, for example. You can also click into each individual note to see where all the relevant data is coming from. So this gives you the ability to adjudicate results really quickly. In addition, you can click into this tree, see the reasoning for why the clinical trial is eligible, because the date of birth matches the cancer has cancer in the breast, and they have the appropriate age. But you can also click on this tree to now see all the relevant data points for their age, cancer sites, and breast cancer. And so this is really impactful for us, right? We can now take complex phenotypes, decompose them into their atomic units of abstraction, review the results, and then review kind of where someone might match or not over time. Um, well, we have a fantastic question. Does the schema need to be built by your team, Brim, for each medical project, and how does that work? I'm going to answer that live. So that is a fantastic question. So you might be saying, all right, Dan, you created this once. That's great. How do I go ahead and create this more generally? So for that purpose, I want to bring up a clinical trial. You have, in this case, a HER2 negative breast cancer clinical trial that we run at Vanderbilt. And as many of you have probably seen clinical trials over the years, there's a long list of criteria. Whether they have HR positive metastatic breast cancer, HER2 negative, and here, the list goes on. It goes long. This document goes on and on and on and on. Okay. But let's say you have this is the example I used earlier in the slides. They're eligible for this drug if the patient received taxane in a neoadjuvant setting and it's been 12 months between their last completion of treatment with curative intent, date of primary breast tumor surgery, or the date of the last neoadjuvant chemotherapy, whichever occurred last, and the first documented local or distant disease recurrence. Again, that's a mouthful. And again, this is one 7A of like 30 different criteria for matching. So the question was, how do I set up my variables in Brim? Why we are so excited about this democratized process is literally you can go into Brim and say, I want to go create a new variable. And you can literally copy and paste your text. I want to define a variable that answers these questions. Moreover, I want to define a variable that if this requires multiple steps to review, decompose it into all the different steps that are needed to abstract that data going forward, such that we can answer the result. And so here, the system has taken the raw text above and produced a tree. At the top level, it's are they eligible for these drugs? The next level was taxane received. Then the next level is time since these events. And then within that, we have, return true if the date of recurrence is minus the date of last treatment is greater than 365 days. And then you have these two date of last treatment and date of recurrence variables. So we can build this tree. And if we like the tree, we can now say generate all the variables that are needed to decompose that. And so take a complex phenotype. Now, for each one of those, we are building out the instructions for all those different variables. So we have a Boolean variable that references these other variables. This taxane variable has a Boolean value that determines yes or no if they had taxane. And then you have a time since treatment variable that references these date of recurrence and date of last treatment variables. And then within the date of last treatment variable, you have a timestamp variable that has instructions on how to reference those variables that returns the latest date from those variables. And then we also have a date of recurrence variable. And, I'm not going to tell you these are perfect, but they give you a tremendous starting point. And with the save of a button, we've now created essentially a variable tree that now allows us to execute this charts abstraction protocol immediately. And so really the protocol in PDF can be converted into variables. Those variables have their own instructions and execution. Brim orchestrates that to abstract the values, and then you can review the values and go. And within minutes now, you can be doing this versus what otherwise would take maybe weeks, months to execute for this. And we can even take this to the extreme. We have teams that are, I kid you not, taking the entire clinical trial protocol, just taking all these criteria, throwing it into Brim. Let me move up a little bit here. Taking the entire criteria of an entire clinical protocol, and saying eligible, and defining all the variables that are needed for the clinical trial. And yes, this might take a minute or two, but we're able to define these protocols pretty quickly, and really get people running and going forward. And so we're really excited because, again, we're trying to democratize chart abstraction. So anyone in the organization that has the definition of what they want to abstract can go ahead and abstract that data today, without needing to know how to program, without needing to kind of rely on a developer and a 6-month dev cycle to build something. So given those large instructions, we now have all the age criteria, the tumor tissue variable, the HER2 negative status variable that's based off the recent biopsy date, their chemotherapy candidate, um, their therapy lines, their prior target therapies, all these other variables that need to be defined, uh, first line of endocrine therapy, start date, et cetera. This facilitates that for you, so your team can get running. So I know I'm at time today. I want to pause, make sure there's some time to answer some questions, um, and go from there. There was a question, how easy is it to modify the tree? Um, Pretty easy. You can provide instructions to say either tweak the tree based off some feedback or generate a fresh tree. You know, um, you know, ignore life expectancy, or include life expectancy after enrollment date. I don't. The point here being is that you can give it feedback, and based off that feedback, it can iterate and help you define the tree, or you can modify the tree itself. And so this is really a powerful tool for organizations to run, and kind of go. And so we're really, really excited. Brim, to be clear, is already deployed at Hopkins. And so it is available for use in certain situations. And we're really excited to potentially partner with a bunch of Hopkins colleagues to kick the tires, and provide feedback on what we're going to do today. What is the pushback on this type of technology? Um, there's pushback in healthcare organizations today for a number of reasons. One, making sure you have the appropriate governance review. Two, have you validated the results? And so there we've rebuilt the tree, and uh, there we've added some life expectancy criteria. Um, One of the big things we talk about is how do we validate the results? And so we actually can upload training data directly into the tool if you've already loaded and done some historical data, um, uh, manually labeled some historical data in the past, so that you can review the results um, directly in the system. And so this kind of allows you to validate the system. So what's the pushback? Validating the results. How do I put it into production safely? If the system fails, how do I make sure that it fails in a safe way such that the patient gets better care or higher levels of care? How do you choose the right projects so that people can safely use this type of technology? But I think those are the big things. The technology is actually not that hard. It's a Docker container running in Azure using your LLM internally, so data never leaves. There is a budget cost to use an LLM. Obviously, LLMs are not free. They require token consumption. And I think those are kind of the biggest issues we face. And then there's just normal processes. But again, Brim is already deployed at Hopkins, and it's available for use today. There's a great question of, does Brim need FDA approval? So we view Brim as a software that does not require medical FDA approval, because it is only providing information that a end user can use and review, and they can make the final determination. We explicitly currently do not use Brim in real-time decision-making situations, or cases where a human is not adjudicating results. Therefore, we typically focus on registries, research, clinical trials, and prep for clinics, because those situations have a human review all the results, the system is not operating. The system can show you where all the evidence was found to make a determination and can guide the system. And we are not going for FDA approval for those reasons today. And we're staying behind that line of software medical as a medical device. But great question. All right. Any last questions as we wrap up today? All right. Well, thank you so much for attending today's seminar. Again, does UCSF decide to use it permanently? I will post reference you to Brim, and they're doing a project on UCSF's website where they're deploying across the institution as a core service. And we've seen over 100 different individuals using Brim to date, literally in a few months. And you know, giving this to people as a core service allows hundreds of people to do research at scale. And it's really fantastic, really, really, really exciting. There was a question, are we using foundation models for building those trees? Yes, we are using foundation models to build the trees as well as do the generation. And again, we are LM agnostic, whether it's Anthropic, whether it's OpenAI, we use any of those models, and we use a bunch of the mini models in most cases. So yes. Fantastic. All right. With that, I think we've answered all my. Oh, we got two more. We use a foundational model. And Monica has clarified a bit more. So Monica has correctly stated, to be more precise, there's an installation of Brim at Hopkins in the context of exploring its use within the cancer center, and it's only has limited availability for now. Broader availability is under further review. That is a correct statement. I apologize if I misspoke. Brim is, yes, internally only used for one case. We would love to have broader collaborations. As a general concept with respect to pricing is roughly equivalent to the price of an OpenAI Pro license per month. So those are roughly order of $200 per month for users to use the software today. Thank you, Monica, for clarifying that. I apologize if I misspoke. Fantastic. All right. And I think we have answered a bunch of the questions. Really fantastic points. If there are anything else, you can send me a message at daniel.fabbri@vumc.org. And I'll put this to all, or daniel.fabbri@vumc.org. And we were happy to talk more about it. So thank you again for everyone for participating today. Have a wonderful day. Would love to collaborate more across Hopkins and Vanderbilt, and have a fantastic afternoon. Thank you so much and have a great day.